Well, good morning, everyone. I'm glad that I have the opportunity to stand in front of you here, in front of this beautiful location. And I'll kick off this morning with a pretty broad and pretty dense overview, not only of what we are doing in Spring Framework 6, not only the state of the Spring Framework world, but very much so the state of the Java ecosystem overall. So there will be plenty of topics that I am going to touch upon, just highlighting what we are doing now in integration with the OpenJDK projects, with larger Java ecosystem efforts, and not only the state of end of 2022 now, but very much the state of 2023. So there are several projects that we intend to pick up in the course of the Spring Framework 6 generation, and this is very, very much my tagline today. So for a few introductory words on the history of things, because it's very much about the present afterwards. Spring Framework 6, of course, is already the 6th generation of this framework, and the previous generations, we are very careful in terms of actually making a major version jump. So we only really do so if there is a major baseline to upgrade to, a major kind of, not necessarily re-architecture, but realignment of the framework with its ecosystem, with its platform, the Java runtime, with its developer tooling, from the Java compiler to everything else that is in use for typical Java-based projects these days. So the first generation got launched in 2004 in terms of its general availability, and we've only reached the 6th generation in well, counting from there in like 18 plus years. So we're really very careful and somewhat conservative in making a major version jump. So let's actually see whether this works. Yeah. So where are we right now? This is what's in production. This is what we recommend to be in production right now. It's the Spring Framework 5.3x generation as the core framework underneath Spring Boot 2.7. So it's very much coupled these days with corresponding Spring Boot generations. The Spring Framework itself, the core framework, is what we traditionally call the Spring Framework, is a broad umbrella, a broad foundation for everything that happens on top in the Spring portfolio. So just to see the relationship, Spring Boot is what you typically use as your entry point, as your means of setup and configuration. Spring Framework is the core foundation, and there are several other projects in between. Spring Data, Spring Security, you name it. So where are we, platform-wise? Spring Framework 5.3x is very much a JDK 8 baseline arrangement, which is the state of the art, the state of the industry. It has been the state of the industry for many years, really. JDK 8 is one of the most important, most widely used generations of Java out there. And it's, in terms of our Spring Framework arrangement, it's coupled to Java EE, as we used to know it, in the Java X namespace, the continuation of the traditional Java EE APIs. That would be Servlet 4.0, for example, JPA 2.1, Java X.Servlet, Java X.Persistence, we'll get to that. That is the traditional arrangement that we come from. That is where all the systems out there basically are or can be at the very moment. Spring Framework 5 had a couple of major themes already, introducing reactive programming. We are going to pick up on that in a moment. Reactive programming, from our perspective, is a tool, a stylistic approach towards maximizing the use of your resources in your runtime system. So modern day Spring Framework is very much about using what you have to the best possible degree, the most efficient way of using the given resources of any particular system, any particular service. To some degree, this shines through the programming model up to the application development. To another degree, we can also optimize within the framework, so transparent to the application without without much impact on the programming model. What we've been launching yesterday, just a day ago, is Spring Framework 6.0. So it's the general availability of the initial release in the Spring Framework 6 generation. What I'm going to talk about now is really Spring Framework 6, that generation, more than 6.0, the release, but I'm going to refer to the status of where we are in terms of what's actually being shipped, what's up next, in more detail. So where is the Spring Framework 6 generation baselined? It's really a pretty high baseline. We are requiring JDK 17 now, so we're really taking a totally modern perspective. We are taking the latest JDK long-term support release as our baseline. JDK 17 has been released in September last year, so it's a bit more than a year old. On an equally important note, we are transcending the barrier to Jakarta EE 9 and onwards. Living in the Jakarta namespace, Java EE has turned into Jakarta EE, all the APIs in there, in particular the ones that we care about, like servlets, the persistence API, bean validation, all those APIs now live in the Jakarta namespace. Basically the same APIs, the same structure initially, just a different namespace, owned by the Eclipse Foundation and not by Oracle anymore, and evolved within a community arrangement at the Eclipse Foundation. So this has some impact that we're going to explore a bit. And there's a couple of major themes, two of which I chose to highlight here. Themes that we chose for Spring Framework 6 ourselves. The ahead-of-time processing, a pretty general approach towards shifting certain computations and preparations to the build time as opposed to doing them at runtime. It's in particular about improving startup time, to some degree also about improving resource consumption, memory consumption at runtime. And another topic we're going to touch upon is virtual threads. That's an OpenJDK project, a new variant of threads that we'll get out of the JDK. So, last but not least, this is the foundation for Spring Boot 3 as the third generation of Spring Boot. Spring Framework 6.0 being the foundation for Spring Boot 3.0. At the very end, I'll explain a little how further releases are going to align there. All right. So let's put it into a timeline. If the JDK 17 baseline may sound a little high initially, keep in mind that we are launching Spring Framework 6.0 GA now, basically yesterday, in November 2022. JDK 17 is already a bit more than a year old. Not only that, there is JDK 18 in the meantime, there's JDK 19 in the meantime, 19 being important because it includes the first preview of virtual threads. There will be JDK 20 in just a couple of months, and in less than a year, 10 months from now, there will be JDK 21, and this will already be the next long-term support release of the JDK. So in case this arrangement sounds a little compact here, it did actually change. Initially, every 3 years, there would be a long-term support release of the JDK. This has been changed shortened to 2 years. Every 2 years, there will be a long-term support release. 17 and 21 using this model for the first time. So Spring Framework 6.1, I can preview so much already, is planned to be released in November 2023, a year from now. This will already be a world where JDK 21 is available as the then current long-term support release. And from that perspective, JDK 17 almost sounds like a conservative baseline already, doesn't it? It's then the previous baseline already. All right. Just a few highlights of not what Spring Framework 6 itself does, but what JDK 17 provides as a baseline arrangement for us. If you'd like to explore this in more detail, there's plenty of resources out there. The most important part is the JDK 17 as a cumulative feature set beyond Java 8, basically. Between JDK 8 and JDK 17, a lot has happened at the language level, at the core library level, even in the type system with the introduction of what's called now record types, records, and as a rather minor feature set of classes. And, well, the introduction of the module system and the evolution of the module system from there. All of these Java platform features can shine through to Spring Framework applications. I strongly recommend embracing them. So part of the reason, at least to the degree that they make sense to for your purposes, part of the reason why we have such a high baseline is because we really want to expose all the goodness in Java 17 and higher to your applications. I admit we also want to expose it to our framework. So Java 17 as a core foundation, as a core reference, a baseline, also allows the framework itself, the framework code base, the framework APIs to take maximum benefit from JDK 17 features. There's a few features that are more important to us than others, say records integration, for example, for data binding. Language usage is mostly transparent. Using new language features against Spring Framework APIs works just as is in most cases. For the module system, if you choose to use it, we do dedicated module path scanning in Spring Framework 6 now, rather than standard class path scanning. Looking at these, the module system has the least impact, really. The biggest value to be reaped, to be unleashed in terms of the Java platform features is certainly in the language and in the core libraries, and with records if you choose to make them a part of your model. So this is empowering our ability to evolve the framework very much as well, in particular as a baseline for further evolution. We are going to remain compatible with JDK 17, but there is already 19, there will be 21 next year. We are putting ourselves as framework providers into a position where we can evolve from where we are now to embracing JDK 19, to embracing in particular JDK 21 as the next long-term support release. And there's quite a bit on it already in those releases that we are picking up, that we are already providing some early support for, that you can already experiment with if you're using JDK 19. As of JDK 21, we expect some of those features to become standard production features in the JDK, because initially they are all previews, like virtual thread is still a preview feature. In terms of our timeline, in Spring Framework 6.1, we expect JDK 21 features to be fully supported. This has a bit of impact. If you think about the perspective that I'm taking here, you really should be seeing Spring Framework releases, Spring Boot releases as well, of course, and JDK releases, Java releases, as sort of going along with each other, going along together. So when you're considering upgrading to Spring Framework 6.0 now, to 6.1 next year, consider upgrading your JDK as well. You have to initially for JDK 17 if you're not there yet. But say for Spring Framework 6.1 next year, why not consider an upgrade to JDK 21 along with it? You can do it at your own pace. You don't have to do it initially, but I strongly recommend making JDK upgrades a part of your upgrade plan next to Spring Framework upgrades. It's a different model now. We get a new JDK release every half year. So you're falling behind pretty quickly if you stay on a particular JDK release for too long. Talking about Jakarta EE a bit more, there's the aforementioned namespace change from JavaX to Jakarta. It's not particularly exciting. I'll be very frank about that, very open. It's also not exciting to us. It's a migration that we have to do because the further API evolution, the further evolution of the servlet API, the persistence API, the bean validation API, is only going to happen in the now Jakarta namespace variants called Jakarta EE 9 and higher. By staying on Java EE 8, you're basically locked to the past forever without further evolution. In Spring Framework 5.3, you can still do this for as long as there's a maintenance arrangement for it, for everything that you are using. But really going forward, using the latest generations of providers, you have to move on to the Jakarta namespace, to Jakarta EE9, to Jakarta EE10. There is no choice. It's a major hurdle we have to overcome. It's compatibility-wise, the strongest impact from Spring Framework 5.3 to 6.0 is actually here, because we're making that jump in that very generation. Now, even here as well, just as with JDK 17, Jakarta EE9 may be the baseline, but what you should really be focusing on is Jakarta EE10 already. Jakarta EE10 got released just like a month or two ago, so it is already available. Jakarta EE10 as a set of APIs wouldn't be all that exciting from a Spring perspective. The more important part is those are the APIs of choice for certain providers, for certain third-party infrastructure that Spring applications typically integrate with. Say Tomcat 10, it's based on Jakarta EE9. Tomcat 10.1 is even based on Jakarta EE10 already on Servlet 6. So they're making those moves pretty quickly. 10.0 was Jakarta EE9 based, lived for a year and a bit, it's already end of life. You have to be using Tomcat 10.1 now, and it's Jakarta EE10 based. That's the new world of API evolution that we're in. The JDK moves forward more quickly. Jakarta EE and the providers implementing it, they also move forward more quickly than before. JD12 is still in alpha, but will also be a Servlet 6 Jakarta EE10 release. Undertow is available, Hibernate ORM 6.1. A major factor, a major part of a Spring-based application stack going forward. If you're doing persistence with Hibernate, you want to be using Hibernate 6.1 at this point. That's also what Spring Boot 3 will come with, which is based on, of course, Jakarta.persistence, implementing the JPA 3.1 APIs from Jakarta EE10 already. The world has been moving on beyond Java EE8. So we're even Jakarta EE9, we're also beyond that already. Jakarta EE10 with actual new features in it is already available, and I highly recommend doing a straight upgrade from where you are to Jakarta EE10, along with Spring Framework 6. Jakarta EE9, as a side note, has basically been a feature-free repackaging. It's the same APIs, no new features, just in the Jakarta namespace, easing migration. Jakarta EE10 is the first release in the Jakarta namespace with actual new features. All right. Where are we? To summarize a little what I mentioned in side notes, Spring Framework 6.0 lives in a world where JDK 17 is the baseline, 18 and 19 are available, Jakarta EE9 is the baseline, 10 is already available. You may choose which of those three JDKs that you may run your Spring 6 applications on. You may choose between Jakarta EE9 and 10 APIs. I wouldn't actually see it at that level. I would choose between providers that happen to implement Jakarta EE9 or 10. So don't focus on the APIs, focus on the providers. You want to be using Tomcat 10.1, the latest version of Tomcat, comes with Servlet 6, Jakarta EE10 level. You want to be using Hibernate ORM 6.1, JPA 3.1, Jakarta EE10 level. That's the perspective we should be using going forward. The API level, Jakarta API level, just comes with it. Next year, fast forward from now, in Spring Framework 6.1, we will be living in a world where JDK 21 is the new LTS release. We'll be releasing Spring Framework 6.1 against then a support range of 2 Java LTS versions, 17 and 21. And by all predictive ability that I can have right now, Jakarta EE10 will be in widespread use by then, almost exclusively. We don't expect basically anyone to be using the Jakarta EE9 API level next year. Take the anyone with a grain of salt, right? But say 80–90% of integrations out there will be at the Jakarta EE10 level, JD12 hopefully being final by then. There's Tomcat, JD, Undertow, Hibernate Validator, everything established. in their Jakarta EE 10-based editions. So, a quick coming back to the timeline, where you're already realizing we're specifically talking about this window of time, this window of opportunity between Spring Framework 6.1 and 6.0 and 6.1 very much, because that's where a lot of exciting things are going to come out of preview, out of alpha, into production. With Spring Framework 6.0, we are in a perfect position to pick up everything that will be coming over the next 12 months. Immediately, we set the foundation up to a degree where we can embrace things as they are being released, as they go out of preview. All right, let's move on to the next major theme, to AOT. AOT stands for ahead of time. It's a convenient term to refer to any further steps taken at build time. You're basically running the Java compiler, and typically at this point you're packaging your application for deployment right afterwards. AOT is about further steps in between. The Java compiler, then a couple of AOT steps, then you package your application into a deployment unit. The Java compiler traditionally produces a pretty simple arrangement, really. Not very optimized. It leaves most optimizations and most assumptions to be made, leaves them up to the runtime environment. That's very much a Java tradition. Java has always been working like this. The Java virtual machine is very good at optimizing itself at runtime, warming up on startup, warming up against some initial requests, and then being highly optimized for the particular usage scenario that the application runs in. This can be very optimal for long-running systems, long-running services. It can be suboptimal if you're starting a Java process only for a limited execution time and then shutting it down again, which includes, of course, any form of dynamic scaling in deployments, in cloud deployments, where certain additional instances of Java-based services are being started dynamically. They might be running for maybe just a couple of minutes. They might be torn down before ever reaching their peak performance optimizations at runtime. So there's different scenarios out there that we deploy Java applications to in this world, and AOT is a tool in the toolbox to optimize for specific characteristics, for specific kinds of deployment units. You're basically saying, I'm willing to take further steps at build time, making further, stronger assumptions at build time, locking down my applications and certain assumptions about it at build time, reducing the dynamic part of it, reducing the flexibility of adapting to the runtime environment, in favor of optimizing startup time, in favor of a smaller deployment unit in some cases, in favor of a reduced memory footprint in quite a few cases. So this kind of framing works for many kinds of deployment arrangements. Standard JVM-based deployments can benefit from AOT processing. You run it on a standard hotspot JVM, but it starts up more quickly. This can be nice. It's less flexible in terms of discovering further classes or further plugins on the class path and so forth, but it starts up more quickly. So how does this work? Specifically for the other elephant, for the elephant in the room, the other topic, the other major topic, GraalVM native executables. AOT processing is de facto a precondition for turning a Spring-based application into a GraalVM native executable. You must run the AOT steps. You must make the assumptions that AOT brings, turning your bin definitions into a more lockdown arrangement, producing a ton of runtime hints before the native image tool comes in, before GraalVM basically takes the output of this and turns it into a native executable. It is a mandatory step in between. So, since we've gone into that already, in GraalVM, this is being called a closed world assumption. You basically lock down the classes that are visible to the application. You lock down the resources, the files that are visible to the application. In the current Spring AOT arrangement, you lock down assumptions about profiles and conditions. You basically pre-evaluate everything that is relevant to your application configuration in order to produce a tighter deployment unit that is able to be turned into a native image. There's the aforementioned runtime hints coming with it. That is also a precondition from GraalVM specifically. In order to produce a native image, you basically turn a very specific variant of the JVM that is able to do very specific things into a native platform executable. This step requires knowledge of every proxy that you're creating, every reflection step that you're trying to take, because the native image will only include what you told it to include. If you tell it, if you don't give it any reflection hints, there won't be any reflective capabilities in it. It can do Java reflection, it can do dynamic proxies, but it needs to be told so at build time. This is part of what Spring AOT does for you. It analyzes a Spring application, infers all those runtime hints, and feeds them into the GraalVM native image afterwards. That's the way Spring Boot does it in terms of a build arrangement for GraalVM native images. Basically, it takes Spring Framework 6, lets it analyze the application with a partial startup, derives all the sorts of runtime hits from it, feeds them into the native image tool, and lets GraalVM do its job. So GraalVM is the current reference point for everything we are talking about. But there is, in parallel to that, or in the background of it, there is an OpenJDK project called Project Laden. This project is a sort of standardization of the approach that GraalVM is taking. It's actually a little different in many ways. It's meant to identify certain kinds of trade-offs that you can make for Java-based applications with an incremental approach where you're willing to accept further constraints for your deployment unit for less flexibility, or you choose weaker constraints, more runtime flexibility. It's basically a choice along different trade-offs that you can make. And a GraalVM-style closed world constraint is really the end of that spectrum, the strongest constraints you could enforce for the tightest deployment unit that you can produce. Now, this hasn't actually been producing any concrete results yet. It's an ongoing project. But since the GraalVM Community Edition releases are now aligned with OpenJDK releases as of next year, we expect closer alignment also between Laden and GraalVM here. There's, another topic really, but related topic, there's another exciting project talking about OpenJDK projects called Crack. This is also effectively an ahead of time step that you're taking, but it works in a different way. You're not running traditional AOT steps and feeding them into a native image tool. You're doing something quite different. You bootstrap your application, you let it warm up. So you've got a running JVM with a Spring-based application in it. Then you kind of stop it for a checkpoint, and you take a sort of snapshot of the runtime JVM as you've encountered it, as you found it when it was fully bootstrapped, when it was initially warmed up. You take a snapshot, and afterwards, you can kind of restore the state of the JVM at that checkpoint very quickly. So you do an initial bootstrap, take that snapshot, store that snapshot on disk, or you maybe distribute it, and in a cloud-based arrangement, every single instance of your service can then bootstrap from that snapshot. This is also a preview project. It's mostly run by Azul, not by Oracle, producing some pretty exciting initial results. So what Project Crack can already accomplish in the early stages that it is in right now is actually pretty impressive. It's not as tight as minimal a deployment unit as a GraalVM native image is, but it can dramatically improve startup time on a regular JVM bootstrap. So this is sort of an approach that we explore in parallel. Next to GraalVM native images, there's also Project Crack for very efficient deployment from a pre-warmed up snapshot on pretty much a traditional hotspot JVM without any further constraints. I mean, obviously, there are constraints here as well because the application started up, in a Spring application evaluated its conditions, made its assumptions, it's fully bootstrapped, so it's fully configured. So you're effectively also taking away certain flexibility, certain dynamic capabilities, but you end up running on a hotspot JVM, which can do everything a hotspot JVM can do. No constraints in terms of proxy generation, runtime class generation, or anything like that. So it's a different approach towards the same goal. You're taking a Spring-based application, you take some steps at build time, you're producing some kind of deployment unit that has some constraints in it, but is more efficient when you're actually trying to bootstrap it. And I'm not giving numbers here because numbers are very temporary. They change every month. Things evolve. It's in the early stages, so no numbers here. But it's a dramatic factor. You can start a Spring-based application that used to take 5 or 10 seconds in a totally sub-second time, right? In 0.5 seconds, very much even less than that. It's even for some scenarios close to what a GraalVM native image can do. So both of them don't just improve startup time by 10 or 20%. They dramatically improve startup time by a factor of 10, 20, in some scenarios, even up to a degree of 50 times faster than before. Just to drop some numbers out there, right? Concrete measures are only to be taken against concrete services. If you want to know what impact this can have, there's early previews of all of these. You can try it against a concrete service, a concrete system, a concrete application that you're building, and see what kind of difference it actually makes for your concrete scenario. I can almost guarantee there will be improvements. The degree of those improvements has to be evaluated for each individual system and service to be deployed. So where are we with this? Well, I've already been referring to previews all the time, so you may already expect that quite a bit of this still has to come together. In Spring Framework 6.0, what we can do right now, what we are shipping with production support right now, is the Spring AOT arrangement, pre-processing of a Spring-based application context at build time for a more efficient startup at runtime and for input to the GraalVM native image tool in particular. This is the foundation for Spring Boot 3's build arrangement in Spring Boot 3.0. It's, from a technical perspective, designed for any kind of deployment arrangement, JVM or GraalVM or even in combination with Crack. But it's at present very much used, designed for and used with GraalVM native images. GraalVM 2020.3, the latest GraalVM release, is a totally fine production arrangement that can be used right now. So if you have a short time frame for production deployment, this is what's already available, or in combination with Spring Boot 3.0, it will be available when Spring Boot 3.0 goes generally available next week. So Spring Boot 3.0 will be final in a week's time from now. This is available for immediate usage. Fast forward by a year, in the Spring Framework 6.1 timeframe, we will already see further evolution from there. GraalVM will do a release with every OpenJDK release every half year, so there will be aligned releases with at least starting from JDK 21, we expect an aligned GraalVM release supporting the same Java level, released at the same time, same support arrangements around it. We'll see where the other OpenJDK projects go through, but from where we stand right now, we also expect the Crack project to be final in that time frame. We'll see. It's run by Azul. It's ready when it's ready. We'll pick it up when it's ready, and we work with the assumption that it will be ready for our Spring Framework 6.1 timeframe next year. Of course, all of these approaches are only as good as they can be used for a complete stack. It's not good enough that an isolated Spring application context works with it. It really needs to work with a complete Spring Boot stack, with Tomcat or Jetty inside, with Hibernate involved, with everything that you're typically using. So if we're talking about production here, we really mean production availability for a complete modern Java stack with Spring Framework 6 and Spring Boot 3 on it. All right, coming back to the timeline for a quick deep breath, and moving on from here to our next topic of choice, virtual threads. Also very timely, because it has been shipping as a preview feature for the first time, as a regular OpenJDK preview feature for the first time in JDK 19, September this year, September 2022. So it's a preview feature, which means it only works with -- enable -preview in Java-C and when bootstrapping the JVM. But it's already pretty complete from our perspective. It does everything it advertises. Virtual threads are a kind of rethinking of what we traditionally know as a Java thread. A Java-lang thread in recent history always meant an operating system thread. Every time you're setting up a thread pool or starting a new thread, the JVM would really start an operating system thread for you. Virtual threads are a different kind of thread, entirely managed within the JVM, using a sort of limited pool of operating system threads in the background. Think like a fork join pool, as many operating system threads as there are CPU cores. Or think reactor scheduling, like in a reactive system, a very limited pool tied to the number of CPU cores available. And then the virtual threads within the JVM are meant to be attached to operating system threads as needed. Whenever they need to perform some actual work, they attach to some operating system thread and are being detached again when they are blocked, when they are pausing, when they have nothing to do. The basic idea behind virtual threads is that in many Java-based systems and Spring-based applications, say Spring MVC applications, Spring Data applications are a very typical example. If you're using blocking APIs, blocking data access APIs, whenever you ask for a certain element to be loaded from the database, you're really blocking. You're waiting for the database driver to do its work, the database to return its results. When the results arrived, your initial thread that performed the call continues from there. That's exactly the scenario that virtual threads have been designed for. Whenever a virtual thread blocks, implicitly, whenever it triggers an I/O operation that blocks, it automatically detaches from the operating system thread and makes the underlying operating system thread available for other virtual threads to perform work on. This allows a much higher number of virtual threads to be run on a JVM than we ever would have worked with before. Of course, with some trade-offs involved as well. You need to pre-analyze the application that you're building. But for a typical web application, a typical servlet-based web application, typical Spring MVC web application, the assumptions for virtual threads are pretty much met in their entirety. You've got blocking APIs in the servlet world for input streams and output streams. You're typically interacting with blocking database drivers underneath. Once again, this needs to be evaluated against concrete applications, against concrete services, for concrete numbers. We do expect significant benefits for a typical Spring MVC database-driven application from the use of virtual threads. This can be experimented with in previews already. It's pretty straightforward to set it up and to test it. We don't expect much performance benefit from between JDK 19 and 21. Basically, virtual threads, either they work for you, they are in preview still, but either they work for you or they don't for your particular system. It's not about further optimizations. It's about the basic assumptions that virtual threads make, whether they make sense for your purposes. the sweet spot here is there are typically no changes to the application code base. We're talking about standard server-based applications, standard Spring MVC applications, standard database, ORM, Hibernate, whatever, interactions. No changes to the application code base, but implicit scalability benefits from a virtual thread setup. The only thing you have to tweak is basically your Tomcat setup, your Jetty setup, your Spring Boot setup in order to make the callback threads virtual. Another scenario, just to not exclusively talk about web applications here, another scenario is messaging applications where, say, Spring's GMS listener containers, the message listener containers, they use blocking, they scale up, and GMS is a blocking API for most purposes, for the most flexible purposes we're using it for. So whenever it hits a blocking spot there, virtual threads are a perfect fit. I expect it to be a perfect fit there as well. Or, of course, for stronger usage of scheduling, cron-triggered or event-triggered execution of asynchronous threads that in turn perform database operations again, maybe. So all of these are, at least in terms of our current prediction, they are a good fit for virtual threads. For the completeness of the picture, and of the understanding of how virtual threads work. Imagine a different scenario. No database drivers involved, purely CPU-bound computation. Like a scheduling thread, a web application thread that does everything from in-memory data structures. No blocking, no I/O, no database interactions. That basically means no benefits from virtual threads. If you have a totally CPU-bound application without any blocking I/O operations, you may switch to virtual threads, but you won't see any benefits because it's the operating system threads all doing the work, no blocking, nothing the JVM can do for you in terms of further scalability. So virtual threads are not a magic tool. They are a pretty simple decoupling of threads within the JVM from operating system threads for scenarios where threads are oftentimes blocked. All right. Nonetheless, we expect a ton of sweetness to come out of the virtual thread arrangement. And there's an obvious question that kind of suggests itself here, and I can only really quickly touch upon it. Is this related to reactive programming? Isn't this sort of the same idea that we are using a limited number of operating system threads and then we let the runtime system use those to the best possible effect? With Reactor and reactive systems, it's about callback-based approaches where the callbacks are only triggered when data is actually ready to be processed, and otherwise they are kind of waiting to be called. Indeed, it's a different way of, a different perspective of accomplishing the same efficiency goals. You're trying to maximize the use of your runtime resources, in particular also of your CPU resources. Reactive programming and the style that comes with it naturally lets you optimize that usage. Whereas with virtual threads, you're basically programming in a sort of imperative way with blocking APIs, and you reap the runtime benefits implicitly. The runtime system sort of does the underlying attaching and detaching from operating system threads for you. So in a world of Project Loom, in a world of virtual threads, reactive programming turns primarily into a stylistic question. Are you doing stream-based processing? Reactive streams, reactive programming is a natural fit for your needs, for your processing style, for your development style. Stream-based processing is what reactive streams naturally are about. If rather you have a traditional database-bound CRUD application where the only use of reactive programming that you consider is for scalability purposes, that's exactly when virtual threads suggest itself as a solution to the problem for you. So taking existing imperative Spring MVC applications typically to a scenario of higher scalability, that's what virtual threads can be useful for in a Spring world. Spring Webflux remains in parallel as a reactive streams processing architecture, also very good at runtime efficiency, but not immediately benefiting from virtual threads the same way. It's a different approach towards the same runtime efficiency. So where are we with this? We've already got experimental setups that can be found on our blog for setting up a Spring Framework 6 and Spring Boot 3 based application with virtual threads. It's a little bit of configuration, not much at all, that sets up Tomcat with a virtual thread-based connector initially, and for scheduling purposes, a Spring executor with virtual threads. Very straightforward to do. Just a few lines of code in a configuration class, really, in Spring Boot 3. The rest of the work is kind of underneath the covers, because there's a few things I haven't been talking about and I don't have the time to talk about, like how does the decoupling of threads works, the attaching and reattaching. There's reasons why a thread can remain pinned to an operating system thread, where virtual threads basically don't work as a decoupled model. If you do too much synchronization at the wrong points, synchronization around I/O operations, you won't be able to reap the full benefits of virtual threads. And to some degree, this is not so much about your application code. It's mostly about the frameworks, the database drivers, Hibernate, and so forth underneath the covers, the web servers even. They internally need to optimize, or have had a need to optimize their locking arrangements in order to be what's often called Loom friendly, virtual threads friendly. Most of this work has happened already, as of Spring Framework 6, as of Tomcat 10.1, as of the most recent generations of database drivers out there. Most of that work has happened already. We expect this to be complete by the time of Spring Framework 6.1, basically. Virtual threads are still in preview anyway, so all of this work in the ecosystem goes on in parallel, on our end, on everybody else's end. We are under the assumption that Project Loom virtual threads can go out of preview in OpenJDK 21 for the next long-term support release. There's no guarantee for that. It's not in our hands. That's a decision that the OpenJDK team needs to make. If it's not 21, maybe it's 22 or 23. Obviously, it would be nice if it's 21 already, but we'll be doing whatever we can, even if this decision is being made late in the game. We are going to do everything we can to provide first-class support for it in the Spring Framework 6.x generation. We expect it to happen for 6.1. We'll basically do it whenever it's in our hands to do it. This means out-of-the-box configuration options mostly. So in Spring Boot 3, you would basically just say, I want an embedded Tomcat with a virtual thread callback model. Thank you, right? So very simple configuration flags, configuration facilities for setting up a Spring-based application with virtual threads. So at the moment, it's a bit of a manual process still. We expect this to become very convenient. All right, one further relationship here, right? We picked it up. We pick up virtual threads right after 19, where they got introduced as a preview, and we expect them to be shipped in 21, ideally, which would allow us to pick them up in our 6.1 release. All very closely aligned, all on a very tight schedule. Now, I've been talking so much about these specific themes. You may already figure that those are topics that have been with us for an extended period. We have been working on Spring AOT, on GraalVM native images for several years with early adopter projects like Spring Native before, now with first-class features in Spring Framework 6 and Spring Boot 3 in the initial releases. So these are very much projects with a lot of history already, a lot of lessons learned. We've been focusing strongly on Spring AOT to some degree in more recent times, experimenting with virtual threads this year. On a very recent note, also with Project Crack, which only really started coming together in a Spring Boot ready form a couple of months ago, so not long ago at all. This reflects our focus, the priorities very much, but of course at the same time, we spend time with features. We refine every corner of the framework. We revisit the entire application framework code base. We do many things in many areas at many levels at Spring Framework 6 level. So to wrap this up, I'm also going to take just a little bit of time of further things that we did in the Spring Framework 6.0 release, mostly unrelated to Spring AOT and to virtual threads or other major topics, even unrelated to the baselining in most cases. What else happened? Of course, we get ideas as we work on things, so it's not totally unrelated, but it's totally usable on its own. We do Java Beans property determination with a different algorithm now. It's configurable. It's by default a different algorithm. You can switch back if you need to, which is significantly faster even for standard JVM bootstrapping, and reduces the memory footprint on startup for a standard JVM application without AOT processing. Any regular Spring Bootstrap, just upgrade to Spring Framework 6.0, you'll get it automatically. No further steps to be taken. For runtime class definitions, we use a complete own fork of cglib now, so this arrangement that we use to produce proxies, specific Spring proxies, configuration, subclasses, and all of that stuff in Spring Framework 6 is now totally in our hands and optimized for our purposes, ready to do Spring AOT, but also ready to do the best job that it can for a standard Spring Framework 6 bootstrap on a standard hotspot JVM for you. When we go to class path scanning, we have a different class path scanning algorithm now. If you start up a Spring-based application and you let it search for your add controller, add repository classes, and so forth in your class path, it uses a different algorithm now based on Java NIO, which is a bit more efficient than it used to be. And on the module system, if you deploy your application as modules, partially or incompleteness, we use a different algorithm again. So a module-provided application deployment unit, we search with a module path scanning API now. This is not only about runtime efficiency, it's also about correctness, about us seeing the full picture of the resources that you ship in your deployment unit. So as a side note, in module paths, modules can be patched, for example, with patching. It's not so clear what you're actually seeing and not seeing. There's well-defined and highly efficient algorithms for that now in place that work for any standard JVM deployment. So no build time steps, just bootstrap your application. This is what's in action now. Even more happened, and I can only really touch upon it very briefly here, even more happened in the web application space. We took the opportunity in Spring Framework 6 to revisit a ton of things that we meant to revisit for a number of years. There's the HTTP interface clients now, to be featured later today, I imagine, that came out of existing arrangements that we had before in the Spring portfolio, but are now a first-class feature at Spring Framework level. There's the Spring MVC and Spring WebFlux support for RFC 7807 problem details, a standard way of reporting problems that occurred during processing an HTTP request back to the client. This is now in as a standard feature out of the box. We revisited our HTTP status code handling. It's now more flexible and more obvious how we process non-standard HTTP status codes in particular. There's a different implementation, totally different implementation for multipart processing, reactive multipart processing in Spring WebFlux now, which has many benefits of its own, but yeah, it's a different algorithm, so we are still learning with a few of those. We are still learning about further fine-tuning from here. But remember that most of those have had exposure to Spring Framework 6 milestones for about a year already. So most of those have been pretty well tested in early adopter scenarios across our portfolio, around our portfolio already. So in that sense, they are not really as fresh as they may sound here. The Reactive Web Client has JDK 11 HTTP client integration underneath the covers if you choose so, as an alternative backend to Apache HTTP client that we traditionally use there. And we have the start of a new observability arrangement, a major topic of its own right that I haven't really been featuring much today, but this will turn into a major effort over the next few years We started now with a minimal but common API for capturing traces and metrics in Spring-based stacks based on Micrometer 1.10 release underneath the covers. We have an initial implementation for our web clients, for REST template and the Reactive web client, where you can see this in action. We expect this to go significantly further from there, not just at the core framework level. It's actually mostly a Spring Boot topic, but as you can see here, observability is a cross-cutting concern. Every component in the stack needs to participate in it, and there are many components at Spring Framework level that potentially can contribute to the observability experience in a typical Spring Boot setup. And this is only the gist of what we do here. There's plenty coming. Even in 6.1, we haven't made a choice yet of what we focus on, but we have a few ideas. Just to highlight one here that I mentioned, we are considering doing an imperative version of our reactive web client, sort of a successor of REST template that uses the same a similar programming model style as web client uses it, a functional style, a builder style, but is entirely imperative underneath the covers. So uses imperative HTTP client interactions, no reactor, no reactive processing. That's why we call it Loom friendly. So what we're really working towards in the web stack is still effectively two variations of the web stack. A highly optimized imperative Spring MVC stack and a highly optimized Spring Webflux reactive stack. Side by side, similar programming model, basically same arrangements, same alignments where we can have them, but a choice that you can make. So if you're taking a Spring Framework 6-based application and you want a virtual thread-friendly Spring MVC stack, there's basically no reactive programming involved that you need to expose yourself to if you don't want to. And there's no reactive components in the stack. It's a totally streamlined servlet-based virtual thread imperative stack. The other stack, the Webflux stack, is reactive from the bottom up. There's a reactor kernel underneath the covers, reactive drivers around it, a reactive web server on it. That's the Spring Webflux stack, highly optimized in its own right. So this is a Spring Framework 5 strategy that we chose. We continue along those lines, and we continue to optimize both variations of the stack and to minimize the footprint of each of those stacks in Spring Framework 6 going forward. All right, so Spring Framework 6 is of course now available as of yesterday. Just highlighting a specific thing here, the relationship to Spring Boot releases. It's not that different really from Spring Framework 5, but just making it obvious here again. Spring Framework 6.0GA, released now, will be the current release, Spring Framework 6.0X releases, until November next year when Spring Framework 6.1 is meant to supersede it. In the meantime, you will get two Spring Boot feature releases. Spring Boot 3.0 next week, Spring Boot 3.1 in May next year. So you'll basically get a Spring Boot feature release every half year, a Spring Framework feature release every year. So every Spring Framework generation is expected to remain a foundation for two Spring Boot generations. It was the same way for recent Spring Framework 5 releases. All right, and of course, also noted here, always production ready on the then available JDK long-term support releases, best effort supported on all JDK releases in between and since. So formally speaking, for production environments, for support reasons, for support considerations, you may want to choose the LTS releases, but we support all the other JDK releases in between and after as well on a best effort, with a best effort model in the open source world. Last but not least, for a bit of a visual impression of our support arrangement, to give you an idea of how this works, Spring Framework 5.3x has an extended support period. This is the open source support period. This is the additional commercial time frame with the yellow boxes. So you can see that Spring Framework 5.3x has a pretty extended support phase overall as the last feature release in the Spring Framework 5 generation. That's the way we are seeing these things. In Spring Framework 6, we're starting a new generation with initial feature releases coming sort of in yearly succession. Spring Framework 6.0 is now, well, the snapshot has been taken like a month ago, but is now available. It's within its open support range. It will have a commercial support range, but it will get superseded by Spring Framework 6.1 rather soon. There is an overlap in the open source support range. There is a longer overlap in the commercial support range, but we really mean you to move forward from Spring Framework 6.0 to Spring Framework 6.1 as you see fit. So whenever you're ready, there's a window of time that we bake into those support timeframes, but we really mean you to move on from 6.0 to 6.1 and then 6.2 and so forth from there. Commercial support timeframes are always attached, but there is none with the length of the 5.3x release, only the last Spring Framework 6.x feature generation. That might be, say, a 6.3 as well. It might be a 6.5. We don't know how far we're going to take this. Only the last of those will then receive the additional extension of the support timeframe that you're seeing in 5.3x here. All right. So that's pretty much all I had for you today. This is where we are. This is where we are. This is where we have just been moving to. This is what we are already working on for your enjoyment next year. Please join the ride. Move forward with us. Make the leap over to Spring Framework 6.0 with the JDK baseline, the Jakarta baseline, and all of these things for a start. Even if you're not considering usage of any of the totally new features yet, this is a significant step that you can take to prepare yourself for everything that you can then choose to adopt. And for everything that there is in Spring Framework 6.0 already, for everything that will materialize over next year towards Spring Framework 6.1. Once you made the upgrade to the initial Spring Framework 6 generation, everything is at your fingertips. Everything is ready to be adopted when you have a need for it, when you see yourself benefiting from it. So we highly recommend taking that jump, upgrading the entire infrastructure, Spring Framework itself, Spring Boot, the JDK, Tomcat, Hibernate, putting yourself into a position to adopt all the goodness that follows from there as you see fit at your own pace. All right, so that's pretty much the end of my storyline for today. Thanks for your attention. I'm around for questions.